people are scared of flying because they are not sure exactly how it works. And honestly, that is a very reasonable fear. One of the oldest human instincts is the fear of the unknown. So when you are sitting in a metal tube 30,000 feet above ground and you cannot explain what is keeping it there, your brain naturally fills with anxiety. The problem is not that the plane is flying. The problem is that you do not know how it is doing that. Because here's what I've noticed. The people who understand how planes actually work are almost never scared during turbulence. The pilot is not scared. He's as calm as a pitch. So each person experiences the flights differently because of what they know. So today we are going to close that gap in knowledge, because by the end of this episode, you will know exactly what is keeping the plane in the air and exactly what turbulence actually is, and also exactly how the pilot controls the aircraft, because by all means, air transportation is the safest form of transportation on Earth. You do not have to stop being nervous, but you will stop not knowing, and that is a start. I am Angelo, and this is the Clarity Podcast. Now, today's episode might sound like a lecture, but I want to believe it is one of those fun kind of lectures. So, the foundation of everything in aviation comes down to 4 forces. And once you understand all of these 4 forces and how they interact, you understand flight. According to NASA's Beginner's Guide to Aeronautics, every aircraft in flight is simultaneously subject to these 4 forces, which are namely lift, weight, thrust, and drag. Now, I'll just give you a quick breakdown of each of these forces. The first one, lift. Now, lift is the upward force that counteracts the weight of the aircraft and keeps it in the air. It is generated primarily by the wings, as air flows over them and under them, and it acts perpendicular to the direction of flight, which is straight up essentially when the plane is flying level. Now, if lift is greater than weight, the plane climbs. If weight is greater than the lift, the plane descends. And if they are equal, the plane maintains altitude. This is the entire vertical picture of how a plane stays in the air. And second thing is weight. Now, weight is gravity pulling the aircraft towards the earth. And everything on board an airplane contributes to the weight. The engines on the plane, the fuel, the passengers, the luggages. And weight acts through a single point called the center of gravity. And pilots and engineers pay very close attention to where that center of gravity is. You load an aircraft incorrectly and the center of gravity shifts, which changes how the aircraft handles. Now, this is why airlines calculate the weight and distribution of every passenger and luggage before departure. They are not trying to be overly dramatic, they are just simply obeying the laws of physics. Now, the third force that contributes to flight is thrust. Now, thrust is the forward force produced by the engines of an aircraft. Jet engines work by taking in air, compressing it, and mixing it with fuel, and then igniting this mixture and expelling the exhaust gases backwards at a very high speed. According to Newton's third law of motion, which states that for every action there is an equal and opposite reaction, this translates that pushing air backwards propels the aircraft forward. Now, there's also the fact that thrust must overcome drag to actually accelerate. We'll talk about drag in a bit. Now, when thrust equals drag, the aircraft maintains a constant speed, but when thrust exceeds drag, the aircraft accelerates. It is important to note that the engines are not the things that lift the plane. They are simply moving the plane forward. What actually lifts the plane off the ground is the wings. And this is why what you call gliders, which are aircraft that have no engines, can actually fly. They have no thrust, but they have wings that generate enough lift. And as long as they have a forward airspeed, which they can maintain by actually descending gradually and trading a high altitude for speed. Now, the fourth and final force that contributes to flight is what is known as drag. Drag is the resistance of the air against the aircraft's forward motion. It is essentially air friction. So, everything about commercial aircraft design is partly an exercise in managing drag. You have the smooth and teardrop shaped fuselage, the retractable landing gear that tucks away after takeoff, the winglets that you see curving upwards at the tips of modern aircraft wings. All of these machines are done in such a way to reduce drag. Less drag means that you require less thrust to maintain speed. And when you require less thrust, you reduce the amount of fuel you are burning. And this also translates to lower operating costs. Now, let us talk about lifts a little more in details. The standard explanation of lifts goes like this. The wings of a plane is usually shaped with a slightly curved top surface and a flatter bottom surface. So, when the aircraft moves forward, air flowing over the curved top surface has a longer path to travel than the air flowing under the flat bottom. And for both of the air to join at the trailing edge, the air on top must move faster. Now, there's a principle that has been used very much in aerodynamics, and this is known as the Bernoulli's principle. And according to Bernoulli's principle, it states that faster moving air creates lower pressure. So you have lower pressure above the wing and a higher pressure below it. Now, this difference in pressure due to the difference in the shapes of the top and the bottom of the wings produces an upward force which is known as lift. Now, Bernoulli's principle is very much proven and it contributes significantly to lift, but it does not give the complete picture, because when you think about it, you might wonder and ask the question, how do some planes fly upside down? And military aerobatic planes do this routinely. So when a plane is inverted, the curved surface of the wing is now on the bottom and the flat surface is now on top. Now, if the wing shape explanation was complete, an inverted aircraft would have negative lift and would fall immediately. But it does not fall, it keeps flying. So that means that something else is generating lift in this case. And what is generating lift in this case is what is known as Newton's third law. Now, when a wing is angled slightly upward relative to the oncoming air, and this angle is actually referred to by pilots and engineers as an angle of attack, it deflects air downwards. So every molecule of air that hits the wing and is redirected downwards produces, according to Newton's third law, an equal and opposite upward force on that wing. So you push air down and the wing is pushed up. This works regardless of the wing shape. It works with flat wings and it works even when the wings are upside down. So as long as the pilot adjusts the angle of attack to compensate, it works even with a piece of paper, which is why you have paper planes that fly, despite having no aerodynamic wing profile at all. Now, the accurate, complete explanation of lifts require both mechanisms working together. Bernoulli's principle explains the lift generated by the pressure difference created by wing shape and airspeed. And then Newton's third law explains the lift generated by the deflection of air due to angle of attack. Real aircraft use both of these principles simultaneously in proportions that vary with speed, wing design, and flight conditions. Now, let us quickly walk through what is actually happening at takeoff and what happens from the moment the aircraft starts moving on the ground to the moment it reaches cruising altitude. Because takeoff is where all the four forces comes into play. Now, the aircraft begins moving or taxiing to the runway under its own engine power at a low thrust. And before this happens, pilots calculate three critical numbers before leaving the gates. The first one is known as V1, which is also known as the decision speed. Now, below this V1 number, if something goes wrong, the pilot can abort the takeoff and stop on the runway. But when the plane is moving above V1 number, the aircraft is committed to flying because there is no longer enough runway remaining to stop safely. Now, the second number calculated is what is known as VR, or rotation speed. This is the speed at which the pilot pulls back on the controls and raises the nose of the plane. Now, the third number is known as V2, which is the takeoff safety speed. And this is the minimum speed at which the aircraft can safely climb even if one engine fails. Now, these speeds are different for every flight because they depend on the weight of the aircraft, the temperature of the air, the altitude of the airport, the length of the runway, and the wind direction. Now, once cleared for takeoff, the pilot advances the throttles, the engines spool up, the thrust builds, the aircraft begins accelerating down the runway. Everything you feel during that acceleration is exactly what comes to mind. The aircraft is trading time for speed. It is building the airspeed the wings need to generate lift. As the aircraft passes through VR, the pilot pulls back on the control column, the elevators on the tail tilt up, and the tail is pushed down. The nose rises, and the angle of attack of the airplane increases. The wings, now meeting the oncoming air at a steeper angle, now deflect more air downwards, and lifts build rapidly. And at some point in that sequence, and this happens faster than most people expect, lift exceeds weight, and the aircraft ultimately leaves the ground. After a while, the landing gear retracts automatically, and usually this happens almost immediately because the landing gear only stays there and serves as a significant source of drag. Now, by the time the aircraft reaches its cruising altitude, all of the four forces we discussed earlier are now in balance. What is happening now is that the engines are producing exactly enough thrust to maintain speed, and then the wings are generating exactly enough lift to maintain that altitude. All the pilot has to do now is use the control surfaces on the airplane to manage its attitude. Now we'll talk about those control surfaces. I believe by now you understand what is keeping the plane in the air. Now let us talk a little bit about how the pilot actually moves the plane around. First of all, an aircraft moves in 3 dimensions around an imaginary set of axes, and all of these axes intersect at its center of gravity. The first axis is the longitudinal axis, which is also known as roll or roll movement. And this runs from the nose of the aircraft to the tail of the aircraft. And then rotation around this axis tilts the wings from side to side, and it is controlled by what is known as the ailerons. The second axis on which an aircraft can move is the lateral axis, and this movement is known as the pitch movement. This axis runs from the wingtip to the other wingtip, and the rotation moves the nose up or down and is controlled by what is known as the elevators. And the third axis is the vertical axis, and the movement is known as yaw. The axis runs vertically through the aircraft. Rotation moves the nose left or right and is controlled by the rudder. Now, there is a lot of fascinating and interesting information about this particular section of the episode, but I'm afraid if I continue discussing about it in details, I might bore you. So I'm just going to stop here and we'll talk about turbulence. So when I introduced the episode, I spoke about some people feeling anxiety when it comes to taking flight. And one of the major reasons for this is they may have experienced turbulence in the past and it's scared them. But I believe with a deeper understanding of what happens during turbulence, that anxiety should abate. So let me explain what is happening. You should know that air is not a smooth or uniform medium. It moves in currents, pockets, and columns. There are what are known as updrafts, which are columns of air moving upwards. There are also downdrafts, columns of air moving downwards. There is also the wind shear, which are sudden changes in wind speed or direction at different altitudes. And then there is also what is known as thermals, which are columns of warm air rising from the heated ground. And all of these contribute to turbulence. There is also what is known as clear air turbulence, which is turbulence in otherwise cloudless air. And this is caused by jet streams and atmospheric wave activity that is invisible to the naked eye. Now, when an aircraft flies through any of these pockets of unevenly moving air, it bumps and shifts, and the nose of this aircraft might pitch slightly, which can also mean that the nose of the aircraft can move in the lateral axis. And the wings also of the aircraft might rock. And sometimes you might feel a sudden drop, which your body can interpret as the plane falling. In this case, the plane is not falling. What you are feeling is the aircraft encountering a pocket of descending air that momentarily reduces the lift being generated. And this causes the aircraft to move downwards briefly before the aerodynamics corrects. You should also know that modern commercial aircraft are designed to handle forces far beyond what turbulence provides. The structures of aircraft wings are tested to extreme loads far exceeding anything encountered in normal or even severe turbulence. Sometimes you see the wings of an aircraft flexing during turbulence. This is intentional. Rigid wings would actually transfer more stress to the fuselage, and so these flexible wings absorb the force of turbulence. Now, even in severe turbulence, which are quite extraordinarily rare, the worst thing that can happen is unsecured objects moving about and falling in the aircraft, and occasional injury to the passengers who are not wearing their seatbelts. So, the best thing you can do while in an airplane is to fasten your seatbelt even when the seatbelt sign is off. Clear air turbulence can actually appear with no warning at all, even in perfectly clear sky. The seatbelt is the single most effective thing you can do to protect yourself during unexpected turbulence. The aircraft for sure will be fine. The question is whether you will be in your seat when it encounters that turbulence. So, to summarize, how does a plane actually fly? A plane flies by having four forces being in constant conversation. Lift pushing the plane up, weight pulling the plane down, thrust pushing the plane forward, and drag resisting forward motion. For a level and good flight, lift must equal weight and thrust must equal drag. You adjust any one of them and the aircraft moves. And then lift is generated by two mechanisms working together, the Bernoulli's principle and Newton's third law of motion. Also, pilots control the aircraft through three sets of surfaces: the ailerons, the elevators, and the rudder. Now, this entire system is an extraordinary piece of coordinated engineering that the Wright brothers began in 1903, and it has been refined continuously ever since and has only gotten better. Also, the next time you experience turbulence, you should not be afraid, because the aircraft is simply encountering uneven air and it is doing what it was designed to do, which was to flex, absorb, and continue flying. And after listening to this episode, I hope that the next time you board a flight, you relax and know that you are in one of man's greatest engineering invention and you are in very, very safe hands. This is The Clarity. Now, this has been The Clarity Podcast. I am Angelo, and if this episode has cleared up anything for you as regards airplanes and how they actually work, please share it to one or two persons. It might be of help to them. As always, follow us on X. Our handle is in the description of the episode. Also, do well to send us any topic suggestions you might have to our email. The email address is also in the description of the episode. See you next week, and until then, think clearly.